6.7, perform similarity transformations. Okay, transformations we talked about way back in chapter 4 when we did translations, reflections, rotations. This time we're going to talk about ones that are similarity transformations, okay? And we actually have a new one and a different one. So because things are similar and not congruent, we are once again going to look for our congruent angles and our proportional sides. So don't forget, transformation is any type of change to a figure, okay? Now, one key thing to remember from back in chapter 4 is all of those when we translated, which means we slid it across the graph. When we reflected, we flipped it across a line. When we rotated and we turned it around a point, every time we did that, the figure stayed exactly the same size. The sides were all the same, the angles were all the same, and that kept it congruent, and that's why we did that back in chapter 4, because they were congruent transformations. This time, they're similar transformations, so we're not going to translate, we're not going to reflect, we're not going to rotate, because that would keep things the same. This time, we're only keeping things similar. So the type of transformation we're doing today is called a dilation, okay? A dilation is a transformation that stretches or shrinks a figure to create a similar figure. So now we're keeping the same shape, but we're going to change its size, and that's where a dilation comes in, okay? Some of you might remember the word dilate, maybe if you've ever gone to the eye doctor and they say, well, we want to look closer in your eyes, and they dilate your pupil, and that makes your pupil bigger so that the doctor can see into it better. Okay, so dilate changed the size of the pupil of your eye. Okay, we have a center of dilation is the fixed point from which a figure is enlarged or reduced. And as we graph, I'm going to point that out a little more and so you understand what that center of dilation is. So usually on a graph, that point is going to be the point 0, 0, the origin, okay? It could be different. And we can do dilations off of a graph, but just know there is always a point of dilation. And, okay, so you think about, well, when my eye gets dilated, what's my eye? It's actually the very center of your pupil, and when they dilate it with that medication, it keeps it from the center. It just makes it bigger. So often the center of dilation can be in the figure itself, and so you don't really see that point. But as you see it on the graph, you'll notice what happens with that center of dilation. Okay, we have a scale factor of dilation. This is the ratio of the side length of the image to its corresponding side length from the original. Because it is the ratio, we're going to see it as the image over the actual. Okay, that's how we're going to see scale factor. So it's going to use those rules of, we're going to, no, I forgot what I was going to say there. We'll do image over actual. When we get to it, I'll remember it hopefully. Okay, reduction. If the scale factor is less than 1, we're going to reduce something. We're going to make it smaller. Okay, so what kind of numbers are less than 1 that would make it smaller? Fractions, right? Like 1/2. Something where the top number is smaller than the bottom number. Decimals, right? Like 0.5, right? Anything that's smaller than 1 as a decimal will reduce that. Okay? The one group that we often forget about, I might use it a little bit more because I use a copy machine. And if I take a paper to the copy machine and I say I want to reduce this, I want to make it smaller, my copy machine doesn't give me 1/2 or 0.5 as an option. It gives me percents. It says, what percent would you like this? So what kind of percent is less than 1? Well, anything less than 100%, right? 100% is like the 1. And then anything less than that. So it would be something like 50% or something like that. So anything that's less than 100 will be a reduction if it's in the percentage, okay? So on the flip side, the enlargement is if the scale factor is more than 1. So what kind of numbers are more than 1? Well, you can still do a fraction, but this time make sure the numerator is larger than the denominator. That number is bigger than 1, and it's going to enlarge the figure, okay? A decimal, right? Something that's larger than 1. What about in the percentage range? If it's going to be larger than 1, it needs to be larger than 100%. So we just make up something and we get something larger than 1, okay? So it's important to be able to see it in all of the fractions, the decimals, and the percents, what those numbers look like. Okay, coordination, I just joined those two words, coordinate notation for a dilation. Okay, we had coordinate notation that we used a lot for translations back in the first semester. Right here is what I want you to see for your coordinate notation. Remember, that tells me when x, y, the point, whatever it was, goes to, and it's kx and ky. So k is the scale factor, okay, whatever it is. And what this means is k multiplies times x, and k multiplies times y, and you get your new coordinate, and it's going to be a change number, okay? It's not going to look like the first one because you're multiplying it by something other than 1. All right, so the second part of the rule here, if between 0 and k is 1, which means it's less than 1. By the way, we don't go negative scale factors, okay? So when I say less than 1, I don't mean in the negatives. I mean between 0 and 1. The dilation is a reduction. And if k is larger than 1, then the dilation is an enlargement. Okay, so a page here full of rules, full of ideas. Let's go practice them now on the following pages, okay? So I'm going to draw a dilation with a scale factor greater than 1 to start with on this first example. Okay, some notes here in the margin that are important to just kind of review and remember and will help us as we go. I have the advantage on my notes. I use a lot of colored pens. If you're just doing things in pencil, and especially when it comes to a quiz or test later, you're going to be working only in pencil. It's nice to be able to show how I know something is the original and how something is the image, okay? So some ideas here. Original figure, make it a solid line, name it like A, B, C, D, and then the image, make it a dashed line, and we call those the prime, if you remember, like A prime, B prime, C prime, D prime for the first change. If there was a second one, it'd be A double prime, B double prime, C double prime, D double prime, all those good things. But these are ideas that you can use on your graph so you know this, which, by the way, on my first example, they want me to graph LMNP. I'm going to change this to A prime, B prime, C prime, D prime, because I think it's just easier to stick with the same ones so we know where the changed point went to, and I'm not calling it something different. Okay, so let's start on our graph by graphing the original, okay? So they give me the coordinates up here at the top of the original, A, B, C, and D. So A is at 2, 0. Always, always, always label, okay? So we know where things are going. B's at 6, negative 4. C is at 8, 2. And D is at 6, 4. All right, so there's my original. And we're going to join those with solid lines. Okay. And then we're going to now use our scale factor. Okay, I'm just now looking at the title across the top of this says, draw a dilation with a scale factor greater than 1. And then it gives me a scale factor of 1/2. So I really don't know why it says that. We'll just say with a scale factor. Okay, I have a scale factor of 1/2. So that is my K, okay? So what that means is when you think of KX, KY, is I want to do 1/2 times my X. I want to do 1/2 times my Y. Everything gets multiplied by that scale factor of 1/2, okay? Now, I'm going to overwrite this. I know some of you are familiar with this where I show all the work so you know where I'm going with it. When you do this on your own, if you feel comfortable, you don't have to show all this work. So for A prime, I'm going to take 1/2 times my X, which is 2, okay? Then I'm going to take 1/2 times my Y, which is 0. Okay, so 1/2 times 2 is 1. 1/2 times 0 is still 0, so A prime is 1, 0. Okay, I'm going to stop quick before I forget to do this. I have that big figure A, B, C, D. When I see 1/2, should that do an enlargement or a reduction? 1/2 is smaller than 1, so it looks like we should have probably a reduction, right? Because we should get smaller. Okay, now, the question I always ask, because our brains have a picture in our mind already. When you picture this reduction, where do you see this new figure going to be? And a lot of people will tell me right here that they think that this is just going to shrink right inside itself. Okay? So that the new figure is just going to be like right in here, but it's going to be a lot smaller. Okay? So I kind of want you to just keep that in mind, that question in mind, as we go through and we do the math and then we figure out where this is going, okay? So I don't ask you that question to sit there and go, ha ha ha, you're wrong. It's one of those things that our brain is thinking something and we have to train our brain to have the right thought. So it's okay right now, keep thinking what you're thinking, and when we get done, we're going to come back to this question. Okay, so I found my A prime is at 1, 0. So here's my new A prime, okay? B. Well, B was at 6, negative 4. So I'm going to take 1/2 times my 6, and I'm going to take 1/2 times my negative 4. Well, 1/2 times 6 is 3. 1/2 times negative 4 is negative 2. Really, I'm running out of room here. Okay, 3, negative 2. 1, 2, 3. Okay, here's my new B. Okay, C was at 8, 2. So I'm going to take 1/2 times my 8 and 1/2 times my 2. 1/2 times my 8 is 4. 1/2 times my 2 is 1. So here's my new C. And then my final one, D, was at 6, 4. So I'm going to take 1/2 times my 6 and 1/2 times my 4. So my scale factor gets multiplied by everything. So 1/2 of 6 is 3. 1/2 of 4 is 2. And there's my new D. Okay. I'm going to dash the lines there in between them. And definitely it looks smaller. Now the question is it in the middle of the figure? And the answer is no. So this is what we need you to think about. I talked about in the definitions the center of dilation. When you are working with these graphs, our assumed center of dilation is always the origin. So here's my origin right here. Think about what it's doing if this had strings attached to it, to every vertex out there, okay? Oops, that wasn't a very straight line. Did not get that good at all. Okay, what a dilation does is from that center, it takes that figure and it pulls on those strings and it pulls it closer. And the closer it can pull it, the smaller it gets, okay? So when I'm pulling that figure, I'm not only making it smaller, but I'm pulling it closer to its center. So that's why this new red figure is not inside my old figure, but it's also closer to the center of dilation, which is the origin, okay? So that's the visualization I want you now to have in your brain instead of thinking when I dilate something, it just gets smaller inside itself, okay? It doesn't really always get smaller inside itself. It could, depending on where the figure started from. But in reality, what it does is it pulls the figure closer to the center of dilation, okay? Now, I know I have a lot going on there, and it's actually hard to see that picture. So let me see if my second picture, if it can look a little bit clearer. Okay, so on my second one, I'm going to start with my original and label it, okay? So A is at 2, negative 1. B is at 4, negative 1. And C is at 4, 2. So there's my original, okay? And now we're going to do a dilation with a scale factor of 2. So think about this. If we have a scale factor of 2, should I be reducing it or enlarging it? 2 is bigger than 1, so it looks like I should end up with an enlargement. Okay, so we're going to multiply every x by 2 and every y by 2. If you're okay with it this time, I'm not going to show all the work. I'm going to do it in our head, but we'll talk about it as we go through it and then write our new ones down, okay? By the way, this is where I should have written enlargement. Okay, so on A, I take 2 times 2 and I get 4. I take negative 1 times 2 and I get negative 2. And that's going to be my new A prime. So I go to 4, negative 2. Oops, right where that B is. All right, that's my new A prime. B was at 4, -1. So my B prime, I do 4 times 2 and I get 8. I do -1 times 2 and I get -2. So there's my new B point on my graph. And then for C, I take 4 times 2, which is 8, and 2 times 2, which is 4, and take it to the graph. And there's my new C point. I can dash those lines so I remember that that's my image. I also use the primes when I named it. Okay, so I took my original and I enlarged it. And think about it again. My center point, I took that figure and I pushed it out farther so it got bigger and it went farther away from my center of dilation, okay? So one of the things we want to know is when we did this, do we keep our figures similar, okay? So we need to check it. We have 3 ways we can check it. We can either try it by angle, angle, side, 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 or side, angle, side to see are these triangles similar. I would love to do angle, angle, but the only type of angles I can ever prove on a graph with what we know so far in geometry is right angles. Can I prove that I have some right angles? I would say I can, right here, right? Angle B and angle B prime, because definitely a horizontal and a vertical line together make a 90-degree angle. So because angle B and angle B prime are both right angles, we know angle B and angle B prime are similar, okay? And by the way, we call these A prime, B prime, C prime. Okay. So now we need to see if the sides around them are proportional. Okay, so it looks like I need to talk about AB and then A prime, B prime. So AB is, I can count that because it's horizontal. Count the spaces, it's 2. Okay, A prime, B prime down here, I count between them 1, 2, 3, 4 spaces. Okay, so I get 4. Well, 2 over 4 reduces to 1/2, right? Okay. BC is on the other side of my right angle, and I can count 1, 2, 3 spaces there. And then it goes to B prime, C prime. So easy when those primes are there to know which ones go together. And I get 1, 2, 3, 4, 5, 6 spaces on that one. And we know 3 over 6 also reduces to 1/2. Or we can cross multiply. I get 12 and 12. They are equal, which means, oops, I don't want to put that not equal sign. They are equal, which means we have equal proportions, equal ratios. So because the lengths are proportional and I have those 2 angles that are congruent, I know by side, angle, side that my triangles are still similar, okay? Moving on to 3rd page. All right, off the graph for a little bit. It says you're making your own photo magnets, and your photo is 8 inches by 10 inches. The image on the magnet is going to be 2.8 inches by 3.5 inches. What is the scale factor of the reduction? Okay, so important as we do this, when we talk scale factors, that we do image over actual. We all need to stay in the same format, so we're going to work on this image over actual. So when I look at this, I started with my photo, which is 8 inches by 10 inches. That is my actual, okay? Then I'm making a magnet out of it, and the magnet, which is smaller, is my image. So it's important to remember, I want image over actual, okay? So it says the scale factor is the ratio of the side length of the image to the side length of the actual, right? So, so this is the picked photo, right? And this is the magnet. Okay, so I need to compare. You either compare the first 2 numbers, the first number with the first number, or the second number with the second number, because we're going to assume that they gave us those dimensions in the same type of order. So if you want to do the first 2, we have 8 inches for the actual and 2.8 inches for the image. I always check, am I in the same units? I am, so I can cross them off. And it says I need to put it in simplest form. Am I allowed a decimal in my ratios? No, I'm not. So we talked about this the other week. If I want to get rid of a decimal, I can multiply both the top and the bottom by some form of 10. I'm just going to use 10 because I only need one decimal place. If there were two decimal places, I'd use 100. And I'm going to get 28 on top, and I'm going to get 80 on the bottom. Is that reduced to lowest terms? I no longer have a decimal, but is it reduced to lowest terms? Not yet. You want to divide by 4? 28 divided by 4 is 7. 80 divided by 4 is 20. And I believe I have a scale factor of 7 to 20. Okay. Let me do a little side note. This was an 8 by 10 photograph. Okay? Those of you that order pictures, and I know with digital nowadays we don't order a lot, but maybe at Christmas you decided to like gift somebody with a photo, and you're like, I want to make a photo. What size do you order? Okay? Or think about your school pictures. What size does your mom like to order? Okay? Some of you order a 4 by 6. Okay? Is school pictures maybe the 5 by 7? All right, I think there's a 3 by 5. Right? What about if you blow it up? Does your mom ever want to get a really big one? Or maybe you had a family photo taken and you get a really big one for your wall, something like that. All right, a 12 by 14 maybe. So we're kind of seeing these picture sizes come through, okay? So if I go on a Photoshop website, Shutterfly, or even, you can get them at Walmart or wherever, there's some standard sizes they give you, and they say, well, which size do you want your photo? So here's my question for you. Here's some common photo sizes. Are they similar? Okay? So let's think about this. If they're similar, we should be able to reduce them all to the same number, right? Or similar numbers, right? 8 by 10 I can divide by 4 or by 2 and get 4 by 5. 4 by 6 is reduced. 5 by 7 is reduced. 3 by 5 is reduced. 12 by 14 I can reduce by 2 and get a 6 times 7, 6 by 7. All right. Are any of those numbers or dimensions similar? No, none of them. So I want you to think about this. Have you ever you had this great picture, right? Somebody gave you this 4 by 6. It was great. You really liked it. It was one of your favorite pictures of you and your best friend. You decide to blow it up and get a bigger one for a gift. So you blow it up, and all of a sudden, part of your head's cut off. And you're like, why? It was fine in the picture I gave it. Well, if this dimension and this dimension are not similar, when you blow that picture up, something has to go, okay? Something is not going to be in the picture, okay? Or maybe it's when you shrink it down, you have more background now. All of a sudden, you're like, wow, I'm a lot smaller in that picture, and there's a lot more trees and grass around me. Because none of these dimensions are similar, when you blow things up or shrink things down, the pictures will not look the same because you've added more length or more width than what the other picture had. So you either get more background or you cut pieces of what you wanted to see in the picture off because the dimensions are not similar. Why aren't they similar? I have no idea. I'd never worked in the photo industry. I don't know why they decided to make pictures in these standard sizes. But you better be careful when you blow things up or shrink things down that you look at what you did first, and maybe you have to move your crop over a little bit or something like that so that you're not cutting out pieces you don't want to cut out. So always do a double check before you enlarge or shrink a picture that you're getting what you want in the picture, or it won't look right, okay? So just a complete side note there, but real life, we do that a lot with pictures. So if you don't want people to cut off or too much background, double check when you do that. Okay, we have another triangle, and we're going to find the new coordinates with a scale factor of 4. So let's start with our original and graph that one. B is at -1, -1. C is at 0, 1. And D is at 1, 0. Don't ask me about C. See, I need you guys to correct me, okay? C is at 0, 1, which is positive, not negative. D is at 1, 0. There, that makes a much better picture. Okay, so there's my triangle. Okay, now I'm going to use a scale factor. Wait, I'm going to write these down real quick because I want to write it. They were written for me earlier, so I didn't worry about it, but now I want to write them down. Okay, this is my original XY. Now I'm going to use a scale factor of 4. So before I start, what should this picture do? That number's larger than 1. That's my K, right? It's larger than 1, which means I should get an enlargement. Okay, that means I'm going to take 4 times my X, and I'm going to take 4 times my Y every time. So negative 1 times 4 is negative 4. Negative 1 times 4 is negative 4. That'll be my new B. Go to the graph. There's my new B. Okay, C. I take 0 times 4, it's still 0. 1 times 4, and I get 4. And I get C prime. All right, D is at 1, 0. 1 times 4 is 4. 0 times 4 is 0. And there's my new D. I guess I could have graphed C. 0, 4, 1, 2, 3, 4. I think I got it right the first time this time. D is at 4, 0. There's my new one. I'm going to... All right. Definitely larger, okay? In this case, it actually looks kind of like it just went around the other one, even larger. But remember, in my original triangle, the origin was inside of there. So it makes sense that if the center of dilation's inside your figure, it's going to look like it just blew your figure up around what you see, okay? All right, in example 3, what is the scale factor of the reduction if your photo is 4 by 5? So just kind of organizing what we know. This time, my photo is 4 by 5. And my magnet that from up above was going to be 2.8 by 3.5, okay? Remember, my photo is my actual, and my magnet is my image. And I want to find my scale factor, okay? So you choose either the first two or the last two. Just because I can, I'm going to choose the last two to work with, okay? But don't forget, I want image over actual. So I need my 3.5 on top and my 5 on the bottom. Can I work with a decimal in my ratio? No. How do I get rid of my decimal? I multiply by 10. So I get 35 over 50. Is that reduced to lowest terms? No. Okay, what can I divide by? 5. And I get 7 over 10. So a different scale factor from above because we started with a different size of photo of 4 by 5, okay? Which doesn't really match my 4 by 6 from up above, but hey, I'm trying to give real-world examples. All right, let's move on to our last page of notes here for 4.6.7 and our last page for the chapter, if you didn't realize that yet. All right, you want to create a quadrilateral JKLM that's similar to quadrilateral PQRS. What are the coordinates of M? Okay, so just so you kind of understand where we're at here, I have PQRS. It looks kind of like this, I don't know, like a little arrow or something. So it looks like P is at 0, 1, 2, 3, 0, 3. Q is at 1, 2, 1, 2, 2, 2. R is at 2, 0. And we'll keep going. S is at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5, 5. Okay. So I found all my coordinates of PQRS. Okay. Now, what looks like is happening is I have this new figure, JKL. I'm missing my last piece. It's out here somewhere, right? There should be something, but I need to figure out where to put it. Okay. So I'm definitely getting bigger. J is at 0, 1, 2, 3, 4, 5, 6, 0, 6. K is at 1, 2, 3, 4, 1, 2, 3, 4, 4. And L is at 4, 0. Okay. We have to figure out where to put M to keep everything in the same ratio. Okay. I need to figure out K. My K is my scale factor, right? That's what it always is. And anytime we find scale factor, what I like to do is image over actual. So don't forget, the blue is my image, okay? And my red here is my actual, okay? So what I need to do is take a number from my image with the same number that goes with it on the actual, as long as my origin is my scale, is my center of dilation, which it is right now, but I'm just kind of throwing that out there, okay? So on J and P, I see my Y is 6 on my image and my Y is 3 on my actual. 6 divided by 3, I think I get a 2. Let's check it on the next one for Q. Well, since X and Y are both 4, I can just check it once. 4 on my image, 2 on my actual, I divide and I get 2. Now my last set of points are in L. My image number is 4 on the X, and on the X on the actual is 2, and I get 2. I think I can pretty confidently say that my scale factor is 2, okay? Because I keep getting that when I do my image over my actual. So if I go to S, and my S is 5, 5, I'm going to do 2 times 5, and then 2 times 5 again, because it's K times X and K times Y. So 2 times 5 is 10, 2 times 5 is 10, and it looks like if I go to 10, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm off the graph by 1 point on each one. It's about right there. If I graph that right there, I have images that are similar, right? It's multiplied by 2. It got farther from my origin. Definitely looks like an enlargement there. All right, so let's try one more of those. All right, I see a 4-sided figure there, W, X, Y, Z. W, X, Y, Z. W is at 0, 2. X is at 2, 0. Y looks like it's at 2, 2. And Z is at 4, 6. All right. Don't forget, this is my actual, right? This is the one I started with. Okay. So now, let's look at our image. And W is going to Q, right? And Q is at 1, 2, 3, 4, 5, 0, 5. All right, X coordinates to the R. And R is at 1, 2, 3, 4, 5, 0. Y kind of goes with my S. And I get 5, 5. And I want to find T, which I don't know it right now, right? Okay. So I have my image and my actuals, and I want to find the scale factor. So remember, to find my K, it's image over actual. Well, once again, they didn't really give us much room for not understanding which numbers are choosing, but I just need to find one value in my image that has a matching corresponding one in my actual, and I can do a 5 over 2. And I think no matter how I do it, no matter which point I choose, I'm going to get 5 over 2 every time. Don't even have to reduce it. I get 5 over 2. So to find my T, I'm going to need to take 5 over 2 times my 4, and I'm going to need to take 5 over 2 times my 6, okay? I'm going to put these over 1, because anytime you have a whole number, put it over 1. So I get 20 on top, 2 on the bottom, which goes to 10. On this second one, I get 30 on top. 5 times 6 is 30. 2 times 1 is 2. Divide, I get 15. So my new point is 10, 15. And I can tell you right now, it is not fitting on that graph, right? It's way up here somewhere in these words. So I'm not even going to get it graphed, but that's kind of where I'm going with that. Actually, it'd be like way over here. Okay. Definitely a worksheet kind of day. We have some graphing to do. I like to see the graphs, but most importantly, I need to see those new ordered pairs. Please, please, please write your ordered pairs, okay? So write your new points, your ordered pairs, and I'm going to know real quick at a glance for those who listen to the notes and follow the notes on their graphs, because if all of your enlargements and reductions are right inside or right on over top the original, I'm going to know you didn't listen to my rule about that center of dilation. So make sure you follow the rules. Write down your order pairs and try that worksheet. And please let me know if you have any questions.